In this next video, we're going to do another example of a double integral over a general region in the plane. So just remember that we have two types of regions that we're looking at, a type 1 versus a type 2 region. With the type 1 region, we're going to, as x is varying from the left side to the right side, we're going to let y vary from the bottom to the top. So a type 1 region has a well-defined top and bottom, and we're doing the slicing vertically, as I like to say. With a type 2 region, we're going to let y vary from the bottom to the top of the region, and for each one of those y values, we're going to let x vary from the left-hand side to the right-hand side, and those x values could be dependent on y. Just like for a type 1 region, as we vary x from the left to the right-hand side, for each x, we're going to let y vary from the bottom to the top, and those top and bottom could be functions of x, could be dependent on x. And that allows us to evaluate a double integral as an iterated integral, either a dy dx integral for a type 1 region or a dx dy integral for a type 2 region. And sometimes we will choose one over the other based on the shape of the region. Other instances, we could be choosing one type versus the other if a region could be viewed as type 1 and type 2 to make the integration easier to evaluate. But notice the key things are that the outer limits of integration we have in yellow here, whether we're doing it as dy dx or dx dy, are going to be constant numbers. They have to be numerical on the outer limit. The inner limits could be functions of x or functions of y, depending on whether we're doing a dy dx integral or a dx dy integral. All right, let's move on to our second example now. So we're going to try to evaluate this double integral of x times 1 plus y squared to the negative 1/2 power. Alright, where r is the region in the first quadrant enclosed by these curves, y equals x squared, our basic parabola, y equals 4, and x equals 0. X equals 0, remember, is the y-axis. It's the vertical line going through x equals 0, which is the y-axis. I have that figure pictured below here, and then we're going to, we'll look at that animation as well in Maple, just to think about the slicing there. Alright, but again, we've got the curve y equals x squared. We're above the parabola. We're below the horizontal line y equals 4, and to the right of the line x equals 0. So that's enclosing that region we have there. All right, so this is our region R. That's enclosed by those curves. Let's look at that in Maple briefly, and then we'll set up and work out this integral. All right, so I've got that over here, and this region clearly has a well-defined top and bottom. All right, so we could think about this as a type 1 region or a type 2 region. All right, and once again, notice that as x varies from the left-hand side to the right-hand side, the height of that slice varies with x. So the bottom and the top vary as x varies. All right, the lowest y value and the highest y value for that slice vary with x, meaning they're going to be functions of x. So we're going to have functions of x as our inner limits of integration if we do a dy dx integral. We can also set this up and do this with horizontal slicing by letting y vary from the bottom of the region to the top, that is from 0 to 4, and then for each fixed y value, let x vary from the left-hand side to the right-hand side of the region. All right, so I'm going to set them up both ways, and then we're going to think about what integral is going to be easier for us to evaluate. All right, just a quick note, many textbooks will write this integral in this fashion, but let's look at it. All right, and they do that to save space, but this is really just x times 1 over the square root of 1 plus y squared. All right, now let's think about the setup for this one. If we think about this as a type 2, or pardon me, a type 1 region, then the way we like to do this is we're going to fix an x between the left side and the right side. Well, we can see in the figure that that's equal to 2. All right, how would we actually get that? We would take these curves, y equals x squared and y equals 4, and set them equal. That would give us x squared is equal 4, which would give us that x is equal to plus or minus the square root of 4, which is plus or minus 2. So there's 2 points of intersection. We only care about the one in the first quadrant. All right, and we can pretty clearly see we're intersecting at 0 also. So for any x between 0 and 2, we'll just put a generic x down there, we're going to let y vary from the bottom of our region to the top. Okay, and the bottom is given by the curve y equals x squared. The top is given by the height y equals 4. All right, so what does this iterated integral look like then? We're going to let x vary from 0 to 2. And for each one of those x's, we're going to let y vary from the bottom of the region, which is x squared, to the top of the region, which is 4. And then we've got x times 1 over the square root of 1 plus y squared, and this will be a dy dx integral. All right, so the inner integral, notice we're varying y from top to bottom on the limits of integration, therefore it is with respect to y. Okay, now let's set it up as a dx dy integral, and then let's see if that's any, and then compare the two and see if one is easier to evaluate than the other. Alright, so doing this as a type 2 region, we would want to think about letting y vary from the bottom to the top, and that's going to go from 0 to 4 in our figure. Alright, and then for our region, we're going to fix a y value, and for any y value, we're going to let x vary from the left-hand side to the right-hand side. Alright, now we have to specifically say what the value of x is at the left side and the right side. At the left side, for every y value, it's going to be 0. For the right side, that's going to depend on the height we're at. And we know this graph is given by y equals x squared. If we're given y in terms of x, we need to, in this case, solve for x by taking the square root. Y is going to equal, or x, pardon me, is going to equal the square root of y. Because we want to know for that fixed y value, for that height we're at, what is the corresponding height, horizontal distance that we're over. That, if we translate that down to the x-axis, is an x value, and that is given by x equals the square root of y. So we're going to let x vary from the left side, which is 0, to the right side, which is the square root of y. Alright, so the double integral, doing it as a type 2 region, would be letting y vary from the bottom to the top, 0 to 4. For each one of those y values, we're going to let x vary from the left side, which is 0, to the right side, which is the square root of y. And then our integrand stays the same. Our order of integration is different. This time it's a dx dy integral. And again, I'm just going to highlight this for a moment, and then I'll get rid of it. Notice the limits of integration on the inner integral are with respect to x. X is varying from something to something, and therefore we're integrating with respect to x. Oops. Okay, undo that. Alright, now let's compare these two integrals. Which one of these is simpler for us to do? Alright, would we prefer to do the type 1 integral we have up above here, or the type 2 integral we have below? If we look at the type 1 integral, we have to integrate with respect to y first. We can treat x as a constant, so this factor of x could come outside the first integral, but this is a very difficult expression to find the antiderivative of. All right, if that was 1 over 1 plus y squared without the square root, that wouldn't be so bad. That would be an arctangent. All right, but this case, that would require a trig substitution for us to do this integral. Now, that's not impossible, but maybe it's easier to do this as a type 2 integral, so let's check that out. If we do it that way, well, now we're integrating with respect to x first, and therefore this whole factor 1 over 1 square root of 1 plus y squared is treated as a constant, and you could even think about taking that outside of that first integral. Alright, so we don't even have, that just comes along for the ride. Integrating, finding the antiderivative of x is very easy. It's 1/2 x squared. So that's definitely the easier way to do that, so let's evaluate it this way. Alright, so we're going to let y vary from 0 to 4. Let's write our antiderivative down now. We have 1/2 x squared, and I'm just going to rewrite the 1 over the square root of 1 plus y squared there. We now need to evaluate that. That's the antiderivative, and now we're going to evaluate this by plugging in x equals the square root of y and x equals 0 and subtracting, and then we have to do the resulting integral with respect to y. Okay, alright, so again, we're plugging in wherever we see x. We have x here. We have to substitute in there the square root of y and 0 and subtract. Alright, so doing that, what does that give us? Alright, next step. We have 1/2. I'm just going to leave that there. I'm going to leave the 1/2 factor over there. I'm going to leave the 1 over the square root of 1 plus y squared. Those are just going to come along. We still have dy there. We're plugging in to x squared. And what are we plugging in there? We're plugging in the upper limit of integration, which is the square root of y, the lower limit of integration, which is 0. All right, now 0 squared is 0. This term goes away. The square root and the square are going to unravel, so that's just going to give us y there. All right, so this integral then turns into the integral from 0 to 4 of 1/2 y times 1 over the square root of 1 plus y squared. And that's always the hardest step. Well, getting it set up is always difficult. Getting the limits of integration correct. The first integral of this integrated integral is the next difficult step here. All right, now from here, this worked out pretty nicely because now you notice you can either write the antiderivative down. If you can't spot that directly, then just maybe try to apply u substitution. This works well for u substitution here. So if we let u equal 1 plus y squared, what's underneath the square root, then du will equal 2y dy. And notice we have in our integral a factor of y and a dy. Factor of y and a dy. So if I divide by 2 or multiply by 1/2, we go to get 1/2 du is equal y dy. Alright, now you can switch the limits of integration also. I'll just leave them there and I'll come back and switch back to y's eventually. How does this help us to evaluate the integral? Now we're still integrating from, I'm going to put this in for emphasis, y going from 0 to 4. This integral is going to turn into an integral involving u. The 1/2 stays there. Alright, y dy we're going to replace by 1/2 du. And then we have 1 over the square root of 1 plus y squared, which is what we call u. Alright, so that integral comes out fairly nice. We can multiply our 1/2 factors and bring that out to the front as 1/4. And then we've got a little bit more calculus to do here. The square root, 1 over the square root of u, let's write that as u to the negative 1/2 power. And then evaluate further. Find the antiderivative. So the antiderivative there is, we need to reverse our power rule here. So we will, again, bring the 1/4 along. We're going to increase the exponent by adding 1 to the negative 1/2. That's going to give us positive 1/2. And then dividing by 1/2 is like multiplying by 2. So we got another factor of 2 in the front. And again, we have to evaluate this by plugging in y equals 0 and y equals 4 after we backfill and back substitute. 2 goes into 4 twice. So this is really then saying we have 1/2 and then the square root of u. And now we have to evaluate that, but one more thing to do. We cannot plug in 4 for u and 0 for u and subtract. We have to backfill this. If we're not going to change the limits of integration, we have to undo our change of variables by replacing u back by y plus or 1 plus y squared to finish this. So we get 1/2 times the square root of 1 plus y squared. You could also change the limits of integration, put it all in terms of u if you like. Either way will lead to the same answer. It doesn't matter. It's a personal preference. Alright, now when we plug in, we get 1/2 times, let's leave the 1/2 in front. If I plug in 4, we get 1 plus 4 squared. That's going to be 17 minus the square root of 1 plus 0 squared. Be careful here that second term doesn't disappear. What does this simplify down to? We get 1/2 times the square root of 17 minus the square root of 1, which is 1. And there's our final result. So in that example, what did we see? We could write that double integral as a type 1 integral, a dy dx integral, or a type 2 integral, a dx dy integral. It turned out the type 2, the dx dy integral, was simpler to evaluate.